Hi, so this is going to be your answer key video where I work through all the problems for your homework packet or your review packet for the test on Friday. Plus there's going to be a little bonus problem at the end as well because I kind of messed up on one of the problems that I was planning on putting in this packet that didn't end up in there. So stay tuned for that as well. If you're looking for a little extra practice, there's going to be one extra one at the end. So we'll get started right away here. Try to get through this as quickly as possible so I can go off and watch The Bachelor. Starting here with number 1, where you are going to do a hypothesis test. And so I'm going to kind of work through the steps of phantoms here. And so when I'm looking at defining the P, I'm looking for what is this question asking me to say something about. And so I'm looking for the true proportion of stations that are having evidence of leakage. And so at the same time that I define what that true proportion is, that P, I'm also going to find that P hat, which I did, you can see on there calculationally, is 7 over 27, which is 0.259, okay? That leads me into question A, which really is asking me to write the null and alternative hypotheses for this. So first thing you have to ask yourself is, am I talking about one sample or two? So in this problem, I just have one sample and one proportion. So my null hypothesis, what we're assuming is true ahead of time, is that the proportion equals 0.4. They say that it's estimated that 40% of gas tanks have that leak to some extent. And then the question asks me, is there evidence that the new program is effective in decreasing that leakage? And so my alternative hypothesis is that we're less than 0.4. Part B asked me to check my assumptions. So if you pull out that green sheet, you'll have those 3 assumptions that you need to check. Number 1, it gave me that it was a simple random sample. I underlined it in the problem, and then put it as my first condition. Second, I'm checking that 27 is less than 10% of all California gas stations. And to me, that feels like a fair assumption. If you've ever been to California, there are definitely more than 270 of those. Third assumption, I need to check my NP and my NQ. Quick double check on yourself here that when you're doing a hypothesis test, you are assuming here that the proportion equals 0.4. You're doing all of your calculations under that assumption here that P equals 0.4. And so down here, when I check my conditions, I use that 0.4. I don't use 0.259. So just double check that you did that to check your NP and your NQ. And it turns out that both of those are greater than or equal to 10. And so my conditions are met, and I can do a 1 proportion Z test. Okay? To test my null hypothesis, I need to find a z-score, my test statistic, and then find a p-value. So you're going to see me work out here that formula for z-score. Starting with my p-hat minus my p from my null hypothesis, so 0.259 minus 0.4, and then all over that standard deviation. We use that 0.4 from our null hypothesis again here. Again, all of your calculations are happening under that assumption. And that z-score, when you type it all into your calculator, take a pause if you need to do that. But that comes out to be negative 1.49. And then when I am finding a p-value here, since I'm doing a left-tailed test, what you type into your calculator is norm CDF from negative 1,000 to negative 1.49. And that's what gives you that p-value. Now, of course, you can also use that stat test menu to do the 1 proportion z-test as well. That'll get you to the same z-score and p-value as well. And so I look at that p-value, and typically, I was getting this question a lot today, is that small or large? And typically, if I'm not given an alpha level, I will use 5% as my cutoff. And so I'm going to use that here. And so my p-value is larger than 5%, which means it's not super duper rare. I'm not thinking to myself, like, for sure, that is super uncommon. Sorry, I'm getting really distracted because there's a giant spider on my ceiling in my apartment right now. I'm going to try to just stop looking at that. But my hypothesis here isn't rare enough for me to have enough evidence to reject the null. So I'm going to say because my p-value is large, higher than 5%, I'm going to fail to reject that null hypothesis. And then I need to put that conclusion in context. Since I'm failing to reject the idea that the p equals 0.4, that means I don't have evidence of my alternative hypothesis. And so here there's not sufficient evidence that the new program is effective in reducing that leakage. Okay, update. I had to pause the video so that my husband could come kill the spider for me.
Nailed it.
Okay, we're back. We're back in business. So the problem here is that you're not always gonna be right. So that 0.6 or that 6.7% chance sometimes means we're wrong. And so since I failed to reject the null hypothesis, if the program actually works, I made an error. If the null is actually false, but I failed to reject it, I made an error. And the null actually being false and me failing to reject it is being a sad sack because something exciting is happening, but I failed to notice it. And so that's a type 2 error. Okay? There's two things you can do to reduce the probability of making this kind of error. So number one, that happens when I fail to reject the null, that type of error. And so if I reject more often, I'm going to make less type 2 errors. So I could raise the alpha level, and then I'll reject more often. Second thing I can always do to decrease my probability of making both types of errors is to increase my sample size. But there are some advantages and disadvantages to both of those things. Increasing your alpha level is going to give you a trade-off. It's going to increase the power of the test because we're rejecting more often, meaning we're going to correctly reject more often. But I will also incorrectly reject more often, and so I will make more type 1 errors just as a result. When you're rejecting more, you'll do it wrong more often, and that's a type 1 error. Number 2 seems like it's all good. You're going to increase sample size. Now, be careful if you increase it too far, then you're going to lose that independence if you go more than 10% of the population. Second thing is that it's going to increase the power of the test while avoiding making more type 1 errors. But anytime you increase the sample size in this context, that means I have to go to more gas stations and check for more leakage, and that's going to cost me more time and money. And so that's just a harder sell when you think about more real-world statistics. Okay, so that is all of the stuff associated with question 1. Moving on to question 2. And question 2 is talking about a margin of error for an interval. And so here, it wasn't written in the problem, but it was supposed to say it was a 10% margin of error. And in the context of this problem, that means, remember, when you're doing one of these confidence intervals, you put your statistic in the middle. And for us, that's either a p-hat or it's a p1 minus p2. And then you're adding and subtract that margin of error, okay, that margin of error formula. And so that 10% is what you're adding and subtracting. So in the context of this problem, it means he believes that the true proportion of Scrabble hands that have A in them is within 10% of his 54% that he found, either direction. And so that builds an interval. When you subtract that 10%, goes to 44%, and when you add it, goes to 64%. And that's a pretty large margin of error going either way. And there's two things that would make a margin of error that large. So if I think about what that formula is, it's a z-score times that standard error, that p-hat, q-hat over n square rooted. And there's two things that could happen to make that whole formula be large. Number one, if your z-critical is large, that could do it. And so a large z-critical gives me a large level of confidence. So again, that's like that I'm 100% sure that tomorrow the temperature will be between negative 100 and positive 200. Okay, that's a really large margin of error because I need that interval to be wider to be more confident. So that's one thing that could be happening. The second thing is that your standard error can be larger, and really that happens, p-hat is pretty much fixed here at 54%, so that can't really change. But your n, since it's on the bottom of that fraction, the smaller the sample size, the larger your margin of error is going to be. And that kind of makes more sense, right? Like the more people in your sample, the less variability you have. It's that whole phenomenon of how you'd be more surprised to have 10 people with an average height of 6'7" than one person with a height of 6'7". The more your sample size increases, the less variability you have, and that's gonna translate to that margin of error as well. Then it asks you about, okay, use that error to describe, like, if that it's predicted that A should appear in 63% of hands. The question C asks you, does this make you concerned that the simulation might be faulty? And explain. Well, if you look at your interval that you created from 44 to 64, 63 is in that interval, okay? And so I'm not concerned that the simulation is faulty since 63 is inside my interval. It fits in, which means my interval is reasonable for the theory that they have predicted. Okay, So that's question 2. And here we are moving on again. Okay. Question 3 says, a champion archer can generally hit the bullseye 80% of the time. Suppose that she shoots 200 arrows during competition. Let P hat represent the percentage of bullseye she gets. And so it says, what are the mean and standard deviation of the sampling distribution model for P hat? So if you remember back to the very first chapter we did in this part, we talked about sampling distributions for proportions and means. And so for proportion here, the mean happens at that population parameter if we know what it is. So here it's saying the population parameter is 0.8. That becomes the mean, the center of your distribution. And then the formula that we have for standard deviation you're very familiar with because we've been using it a lot when we've been doing our 1 and 2 proportion tests and intervals. But it comes from that square root of PQ over N. And here we know the population parameter is 80%. So that's what we're going to use. So it's square root of 0.8 times then 1 minus that would be 0.2 over that sample size of 200. Okay, so I have that standard deviation of 0.028. Just a quick refresher, if this question had been about means instead, the mean of X bar is just that population mean. Okay. And the standard deviation of X bar is to take your standard deviation of the population divided by the square root of N. So those are the formulas you would need if instead of proportions we were talking about the sampling distribution of means. And there's no question about that in the packet, so I just wanted to refresh your memory on that. To check if a normal model is appropriate, you're going to check your 2 conditions. Number 1, your NP and your NQ being greater than or equal to 10. And they both are, so 200 times 0.8 and 200 times 0.2 are 160 and 40 respectively. And so those are both greater than 10. And then you're going to have to assume that each shot is independent of the last. She's not getting any better as she shoots. She's not getting any worse. And so each arrow is independent of the last one that she shot. And so if those 2 conditions are met, then I can use that normal model. So in part C, it asks you to sketch the sampling distribution. So it asks you to sketch basically a normal model using the 68, 95, 99.7 rule. And so basically what I want you to do is draw that picture of a normal model, put your mean in the middle, and then go out 3 standard deviations each way. So go out starting with 0.8 in the middle, and then adding 0.028 or subtracting 0.028 each time you go out. And then you guys know here that between these 2, 1 standard deviation each way is 68%, 2 standard deviations each way is 95%, and 3 standard deviations each way is 99.7%. So I just wanted you to draw that picture of that normal distribution using your answer from part A. And then to find the probability that she gets at least 85% bullseyes, I can just draw that on this picture. And so if I draw that on the picture, I'm going to put 85 on there, and then shade at least means that or greater. And so I'm looking for the probability that P hat is greater than or equal to 0.85. To do that, I need to find a z-score for 0.85, which you can see I did over on the side. I did 0.85 minus that mean in the middle, divided by my standard deviation. Got that z-score of 1.79. And then I'm going to do a norm CDF in my calculator from 1.79 to 1,000. Okay, because I'm trying to go from 1.79 right forever. Okay, so type that on into your calculator. And when you do that, that should give you a probability of 0.039. Okay? And that's that. And again, you could do that same type of question for a sampling distribution of means. You would draw a normal model. The formulas are just the ones that I put in red up near part A. Okay, question 4. This is the one that I kind of messed up. I meant to put on here a test that was a 2 proportion test, but I got confused by the words different and the lower for girls than for teens in general. And I originally, when I was quickly reading the problem, thought it was going to be 2 proportion, but it's not. So whoops. What I did instead is I put a bonus 2 proportion z-test question at the end of this video. So sorry about that, but I didn't want to leave you hanging because there will be 2 proportion z's on your team test and your individual test. And so if you are looking for some practice on that or just to watch through an example, it's at the end of this video. But we'll still do this problem. You kind of already did a 1 proportion z-test at the beginning, question 1. So I'm going to go through this kind of quickly. Again, defining your proportion, your parameter, the true proportion of accidents for girls is what I'm trying to say something about. And then I found my p-hat from the problem is 44 out of 388, or 0.113. Going to go through the phantoms process. I'm going to do it quickly because, again, we already talked through all this in problem 1. Write your hypotheses first. Again, your null hypothesis is always that you are equal to 0.143. And your alternative in this case is I want to know, is there evidence that the rate is lower for girls than for teens in general? So is that proportion less than that 14.3%? Okay. We're going to check our assumptions and conditions. So number 1 here, we're going to assume that they investigated, because the problem says of all the accidents they investigated, this is how many of them were teenage girls. So we're going to have to assume here that they investigated a random sample of accidents. Then I'm looking at 388 has to be less than 10% of all fatal accidents in 2002 when we're talking about. And then number 3, checking that NP and that NQ, again, using your null proportion, not your p-hat, is 55 and 333, and those are both greater than or equal to 10. So that's my checking my things, my assumptions and conditions. And then I'm going to name my test that I'm doing here, which again is a 1 proportion z-test, and the sad face is because, whoops, I didn't mean to do that. All right, so again, you're going to find your test statistic. You're looking for a z-score, subtracting your p-hat minus your p over that standard deviation. And that z-score, when I do all that, comes out to be negative 1.67. And then I'm going to obtain a p-value. Again, I'm doing a left-tailed test here. So when I do it in my calculator, I'm going to click on second vars and do a norm CDF. And since I'm doing a left side up here, I'm going to go from negative 1,000 to negative 1.67. And so that p-value when I do that, see, there's my calculation. My p-value when I do that comes out to be 0.0479. And then I'm going to make my decision and I'm going to write a conclusion. And again, I tend to make 5% my cutoff. Well, this time I'm just below 5%, which means I have a small, rare probability of this happening. And so I'm going to reject. I don't think I'm that unlucky that I just get this value by chance. And what I think is happening instead is that there's something fishy with that null hypothesis. I'm going to reject that. So it starts like this. Because the p-value is low, I reject the null hypothesis. Then I'm going to put that in context. So I'm going to say, if I'm rejecting the null hypothesis, that means I'm feeling like I have evidence that the alternative is actually the truth. I'm rejecting what I thought was true before. And so I say there is convincing evidence that the accident rate is lower for girls. Yay, good job, girls. Then it's asking me, okay, so you got this p-value of 0.0479 over here. And it's asking me, what does that p-value mean in this context? So again, you're doing all these calculations, assuming that that null hypothesis is true. So my p-value is like, assuming that the proportion for girls is 14.3%, what is the probability that I would get a p-hat in my sample of only 11.3%, or even more rare? Okay, and so I'm going to write that out. If the true proportion is actually 14.3% for girls, we would get a proportion of 11.3% or lower only 4.79% of the time, just due to that normal sampling variability. We're not expecting to always get exactly the true proportion in our samples because of variability, but this one's pretty rare. Only 4.79% of the time. That's what that p-value tells us. Okay? All right, let's talk through question 5. Question 5 is asking me to make a confidence interval. I believe it's just talking about 1 proportion. So here on intervals, instead of doing the whole phantoms process, this is where I'm just going to do my panic process. And so it says in 2002, the medical journal, The Lancet, reported that 335 of 573 patients suffering from Crohn's disease responded positively to injections of the arthritis-fighting drug infliximab. And so I'm looking at a 95% confidence interval for the effectiveness of this drug. And so I'm trying to say something about the true proportion of patients that are responding positively with this drug. And so I found a p-hat from the problem of 335 over 573, which comes out to be 0.585. Now, this time in my problem, I'm not going to write a null hypothesis. So anytime I'm doing a thing like an NP or I'm finding a standard error, the only thing I have to go off of is this p-hat. So even though we use p for tests, since we don't have that here, we have to do all of our calculations based on this p-hat value. Okay, so we're going to check our assumptions and conditions. Number one, we're going to assume that this is a representative group of patients. Okay, obviously it's not a random sample. They're all going to have Crohn's disease, but we're hoping that this represents all Crohn's disease patients well. We're going to assume that 573 is less than 10% of all patients in the world that are potentially taking infliximab. Less than 10% of all those Crohn's patients. And that seems like a fair assumption, although to be fully honest with you, I don't know much about Crohn's disease, so I could be wrong about that. But I'm going to operate under that assumption. And then I'm really checking here my NP hat and my NQ hat. Okay, and so those are coming from using this p hat. So I'm doing 573 times 0.585 to get that NP, and I'm doing 573 times the opposite of that, 0.415, to get 238. And those are both greater than or equal to 10, so I'm good to go. I checked my conditions. I'm going to name that interval, which is going to be a 1 proportion z interval, and then I'm going to start calculating it, okay? So you're going to build your interval starting from your p-hat, starting from 0.585. You're going to add and subtract the z-critical that goes with 95% confidence. Now, if you don't remember how to get that, I thought I drew a picture, but I must not have. That one's the pretty common one that you've seen a lot, but you could draw a picture and put that 95% in the middle, and then do an inverse norm of one of your two endpoints in your calculator. And then you're going to multiply that z-critical 1.96 times the standard error, and so that's the square root of 0.585 times 0.415 over 573. And I do that all in my calculator, either as is, or I can do it in my stat test menu for 1 proportion z interval, and that comes out to be 0.544 to 0.625. Then part B asks you to take that interval and interpret it in context. And so here's where I'm going to say I'm 95% confident that the true proportion of, put it in context here, patients with Crohn's disease that are responding positively to infliximab is between 54.4% and 62.5%. Okay? And then part C asks you to say, okay, so that's like your canned response for a conclusion here, but what does that 95% confidence really mean? And that means 95% of intervals that you're making with these conditions. So at this level of confidence with this sample size would contain the true proportion of favorably responding patients. If you do this over and over and over and over, sampling 573 patients with 95% confidence, you would expect 95% of your intervals to capture that true proportion. Just like if you remember back to that Hershey Kisses thing where we all drew our intervals on the board, and about 95% of them captured that true proportion. Okay, so that's kind of what the context of that means. All right, moving on to number 6. We're getting there, you guys. All right, number 6. I left a piece of this out, but it was saying with 90% confidence, this is the one where I drew the picture, I remember now, and a margin of error of 4%, it's asking you for a sample size. And so I left the 4% out of this problem. Hopefully I remember to tell you that, but if not, stop and try it now that you know that it's 4%. And I'm looking at the percentage of students that are binge drinking. And so I'm going to build this margin of error formula. And so again, that margin of error, I'm just going to write that formula in here, is the z critical times your standard error. So p hat, q hat over n. And this problem has a couple pieces to it that you don't know. So you know the margin of error is 4%. So I put that in for my margin of error. I know that I'm looking at 90% confidence. And so that 90% is that middle 90%. And what that means in this case is if I draw that picture, I've got 5% in each tail. And so you can do in your calculator either inverse norm of 0.05 or inverse norm of 0.95. Those are your endpoints. And that should give you either positive 1.65 or negative 1.65. And that procedure of drawing the picture would work for any level of confidence you were trying to do here. Now, it doesn't give you a p-hat. And so when I'm thinking about this problem, it says, how many students must I survey to ensure a margin of error of 4%? So let me think here for a minute. The worst case scenario that would make this standard error as large as it could possibly be on top of the fraction is if I have a p-hat of 0.5. 0.5 times 0.5 is the largest that numerator can be. Anything else like 0.2 and 0.8 multiplied together, or 0.9 and 0.1 multiplied together. Anything else that you could possibly have gives you a smaller p-hat, q-hat on top than 0.5. So if I'm looking for ensuring a margin of error of only 4%, I want to operate under the worst case scenarios here. Okay, so I'm going to leave that top as 0.5 and 0.5, and that'll make sure that my n is large enough to account for even that worst case scenario of p-hats. From here, now you're just solving this equation like a normal algebra problem. So probably most of you can pause, take it from here, and run. But what I'm going to do at this point is I'm going to divide both sides by 1.65. And that in my calculator will give me 0.024. And it's gone on the right side. And then my next step is to square both sides. I'm also going to multiply my 0.5s together at the same time. So I'm going to square both sides, and that cancels out my square root. In your calculator, you get 5.9 something 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 e negative 4. Don't forget that that's your scientific notation indicating that you need to move your decimal place 4 to the left. And then you're just going to cross multiply and divide here to get your n of about 424 people that you need as your sample size. Okay? All right, question number 7 is going to talk about errors and consequences of those errors. So you're looking at this advertising agency. They're trying to get a sponsor for their, a spokesperson for their product, but they're only going to do that if it's known to more than 25% of their target audience. Meaning like you want to find like a good athlete to sell your shoes, or you want to find a good chef to sell your knives, or whatever it might be. Whoever their target audience is for their product, they want an athlete that's known name recognition wise to their audience. And so they've got this null hypothesis of p equals 0.25. That's what they're assuming is true. And they want to see if their person has name recognition higher than 0.25. And they're doing this all at a 5% level of significance, meaning that if their p-value is lower than 0.05, they will reject. And if their p-value is higher than 0.05, they will fail to reject. That's what that level of significance means. They're doing only an upper tail test because they're only interested in finding out if an athlete is well known. They don't want to know if an athlete is very poorly known, and they don't want to just know if they're different. They're curious about knowing if an athlete is popular. So they're only going to do a right tail test here. Okay, so a type 1 and a type 2 error in this context. So type 1, remember, is your Chicken Little. She thinks something is interesting is happening when it's not. So that means my null is true. Nothing interesting is happening, but we're rejecting that idea of boring and thinking something interesting is going on. So in this case, if the null is true, that means that their athlete isn't particularly popular. Okay, that p equals 0.25. They're not greater than 0.25, but we think they are. Okay, so the athlete is not well known, but the company thinks that they are. The question is also asking me to talk about the risk that this error poses to the company. And so the risk here is that they waste money on the endorsement of paying for an athlete that's not going to sell their product well, not have that recognition. Okay, what that means is your type 2 sad sack error is the opposite. Your null is false, meaning that exciting things are happening around you, but you fail to notice it. You fail to reject that null hypothesis. And so this is where if your null is false, that you do have a popular athlete, but you're failing to see that athlete is popular. So they're well known, but the company doesn't think they are. And the risk here is that they're missing out on a well-known sponsor that they could have for their product. So those are kind of the two different risks and then the consequence of each one of those risks. The company is thinking of changing its test so that instead of a 5% level of significance, now they go up to 10. If you think about what that does, that makes them reject the null hypothesis more often, which is good. They're seeing something interesting more often. It's going to increase the power of the test where they correctly identify that something interesting is going on. However, it's also going to increase your chance of a type 1 error. And so you're going to be making more of those errors where you're potentially wasting money on endorsements for athletes that aren't popular to your target audience. Okay, so it's important when you're analyzing errors like this that you're talking about what happens and then what's the consequence to whoever's making the mistake. All right, last question in your official packet, where you're asked to make a 2 proportion Z interval. It doesn't give you a level of confidence. Say I believe 95%, but you can kind of choose here. And then it says their sample is 1,003 randomly selected U.S. adults, and they're splitting them into 2 groups randomly where they're asking them these 2 different questions. One where they say, do you want nuclear energy somewhere in the U.S.? And one where they ask, do you want nuclear energy in your area? Sort of like the not in my backyard phenomenon that they're testing here. Meaning like things that we know are for the greater good, like we want them in the world, but not too close to me if it's potentially a risk, right? And so I defined my two proportions here. P1 I said is the true proportion who are in favor of nuclear energy for all of the U.S. And then P2 is the true proportion in favor of nuclear energy in my area. Okay? And then I found my P-hats and my N for each group. And then I started checking my conditions. So number one, that the groups were randomly selected and split, which they did say in the problem, both of those, and that they're independent of each other. So one respondent's answer to one shouldn't influence what somebody says in the other group. Number two, my 2 sample sizes, if I split that 1,003 in half, neither group I ended up not wanting to cut a person in half. I don't know why they chose an odd number for this problem, but I split it into group 1 got 501 people and group 2 got 502 people. Neither one of those is going to be greater than 10% of the U.S. population, so we should be good to go on that second condition. And then checking each NP hat and NQ hat for the 2 groups. And you can see I showed all my work for that as well, and split those. It says split into half, so I just gave one group, like, when you split a paycheck and somebody gets the extra penny, I did that with the extra person. But all of those NPs and NQs, you can see, turned out to be greater than or equal to 10. All right, so that means I'm good to go to do a 2 proportion Z interval, and I did mine with 95% confidence. And so I'm going to start with the difference between my 2 groups. And I did 0.53 minus 0.4. And then you can see here, I put the whole interval on there, so I did 95% confidence again, which gave me a Z critical score of 1.96. Reminding you that for an interval, we are not assuming that the 2 proportions are equal going in. And so we are not pooling when we find that standard error. Okay, so you are not pooling your 2 proportions together unless you're doing a test. Okay, so you can see in my standard error formula here that the 2 fractions, this one and this one, don't have the same values in them. Okay, I kept the 2 proportions separate. Okay, and then I built the interval. I actually typed it all into my calculator and did it that way, but you should be able to additionally, in your calculator, press stat tests and then a 2 proportion Z interval and get sort of the same thing here. And then I'm going to write my conclusion that compares the 2. And so you're going to see that both of the ends of my interval are positive. And that means that in this case, P1 is greater than P2. So I'm going to kind of put that into context here. So I'm 95% confident that the proportion of U.S. adults who favor nuclear energy is between 6.9 and 19.2% higher than those who want one in their area. And so people who want it in general is generally higher by 6.9 to 19.2% than people who are willing to have it in their backyard. Okay, so that is the end of the packet. If you're interested in doing a 2 proportion Z test, especially if you were gone last Friday, not a bad idea to do so. It is going to happen. I'm going to give you a bonus problem. So if you want to keep watching the video and do this, maybe like if you have extra space on the bottom of that back page of your packet, or if you want to staple another piece of paper on, it's good practice. So this next problem is right here. So it says, are more parents checking up on their teens' online activities? A Pew survey in 2004 found that 33% of 868 randomly sampled teens said that their parents checked to see what websites they visited. In 2006, the same question posed to 811 teens found that 41% reporting such checks. Do these results provide evidence that more parents are checking as time goes on? And so if you want to take a minute to pause and try doing this test, it's really close to the warm-up we did today on Monday. So give it a shot following maybe the warm-up that you did and give it a chance, and then come back and watch this and I'll work it out for you. Okay, so starting with defining 2 proportions here. So the true proportion of parents checking up in 2004, I made my P1. And then the same idea, the proportion of parents checking up in 2006, I made my P2. And so I've got my P1 hat and my P2 hat and my N1 and my N2, and those were all given to me in the problem. Then I need to write some hypotheses. So again, your null hypothesis is always to assume that your 2 proportions are equal, and so that is the difference would be equal to 0. And then it asks me, did these results provide evidence that more parents are checking up on their kids now or in 2006? And so if that's the case, my P2 would be higher than my P1, which makes the difference negative. Now, if you set your things up the other way, if you made your P1 2006 and your P2 2004, then it would be a greater than 0. So it kind of depends how you set this up. The wording is tricky because it's saying more, but really my null hypothesis would be less if I think about what that difference would be. Okay? Check those same assumptions and conditions that you did on the last problem. I'm starting to have a tired voice here, and so I'm going to just let you watch me write them. But you've got that random sampling and independent from year to year. You've got less than 10% of the population, and then checking each one of those NPs and NQs. And here you're almost always going to want to use the stat test menu, and so you're going to need to find those NPs anyway to type into that. Okay, so we're going to do your 2 proportion Z test, and you're going to start that by finding your p-hat pooled. And so here's where on 2 proportion tests only, since you are assuming in your null hypothesis that the 2 proportions are equal, then you want to pool into one large sample. And so I do my successes, okay, which in my first proportion is 33% of 868. Okay, you did that in your assumptions and conditions as well. So 286 plus, and then your successes in the second group is 333. Combine those, and then combine them on the bottom. Your total populations, and that comes out to be a p-hat pooled of 0.37. And that is what you're going to use to find your test statistics. So when you go to find your z-score, you start with the difference between your 2 proportions, and then subtract the 0 from your null hypothesis. And then on this time, on my standard error on the bottom, you're going to notice that the tops of both of those fractions are my p-hat pooled instead of the individual proportions from group 1 and group 2, okay, with the sample sizes of 868 and 811. That gives me a z-score of negative 3.44, and you can also find that by just doing that test menu. Underneath that, you're going to see a p-value that says 2.88, e negative 4, so again, move that decimal place over to the left 4 times. And that is a teeny tiny p-value, which means you can reject that null hypothesis right on out of here. That is super rare. And so because your p-value is small, we're going to reject the null hypothesis. which means I have evidence of my alternative, which means there is convincing evidence that more parents are checking as time goes on their children's online activities. Okay? Hopefully this video didn't put you to sleep in your PJs on Tuesday when you're watching it. Hopefully it gives you some more confidence doing some of these problems to go and do your homework packet. But feel free to come see me in the next couple days should you have questions. All right. Good night, everybody.